Good day everyone. Hi, I am Dr. Hazrina Mansa. Previously, in lecture video, part 1, we have learnt general introduction regarding tall building. By now, we already know how to define tall building, why do we need tall building, how to categorize the tall building, and identify the tall building based on its usage. So, next, we're going to learn on the part 2 of the first topic, that is structural form of tall buildings. Figure shows the design criteria that must be considered in designing tall building. Meanwhile, here are the typical notes that must be considered in designing tall building. Alright, students, how to select the suitable structural form in designing tall building? Any idea? For your information, selection of the structural form involves selection and arrangement of major structural elements to resist loads effectively. This includes a circumflex internal planning, material and method of construction. For example, as you can see in figure 4.1, the weight of the floor framing is influenced mainly by the floor span and is virtually independent of the building height. Meanwhile, the weight of the columns, considering gravity load only, is approximately proportional to the height. As we can see, 10 stories building can usually accommodate wind loading without any increase in weight of steel or member sizes. On the other hand, for buildings which are more than 10 stories, the additional resistance increases non-linearly with height. That's mean, for buildings of 50 stories and more, the selection of an appropriate structural form may be critical for the economy, and indeed, the viability of the building. Another thing that you must consider is the function of the building. For instance, an office building requires open space column-free area, like partitions. Services in ceiling caused story height greater than 3.5 meters. On the other hand, a residential building requires continuous vertical columns and walls repetitive corridor, in which a story height greater than 2.7 meters by identifying the building's function and material used. Therefore, it will provide architect and engineers a comprehensive view on the planning and design aspects. In general, there are 11 different structural forms that can be proposed in designing tall buildings. Bear in mind, at times, if the new concept of tall building design being proposed by architect, thus, there will be another possibilities of structural form that will be introduced. At this moment, the listed here are the common structural form of tall buildings that currently being used. As you can see here, we can either propose braced frame structure, rigid frame structure, infilled frame structure, shear wall structure, wall frame structure, frame tube structure, outrigger braced structure, suspended structure, core structure, space structure, and hybrid structure. Braced frame structure. Braced frame structure is the basic structural form for tall building. In braced frames, the lateral resistance of the structure is provided by diagonal members that together with the girders form the web of the vertical truss, with the columns acting as the chords. The most common type of bracings are single diagonal bracing, double diagonal, chevron, story height knee. This system is commonly used in steel construction. It is both an efficient and economical way for improving the lateral stiffness and resistance of rigid frame system. The bracing will almost eliminate the bending of columns and beams. Lateral loads primarily through axial stress, thus allowing for slender elements. A very well-known example of braced frame structural system can be seen in the Empire State Building. If bracing is used in concrete structure, thus, double diagonal bracing is required. However, the use of bracing in concrete structure is unfavorable. As you can see in this figure, the construction of cross bracing is quite tricky in concrete rather than in steel structure. Such condition will trigger difficulty in segregating the concrete mixture equally, hence will have high tendency to cause honeycomb. Large-scale braced frame is another way of providing bracing in braced frame structure. This can be seen in figure 4.5. However, the presence of either small or large-scaled bracings may obstruct view, thus, As a solution, the braced beams shall incorporate a long wall and partition lifts, stairs or service shafts. Unsuggested also, for bracing to overcross several floor heights, instead of one. Will you prefer this kind of view inside your workspace? In analyzing the braced frame structure, two methods of analysis will be used, namely member force analysis and drift analysis. The next type of structural form that you can propose in designing tall building structure is a rigid frame structure. In rigid frame structure, the behavior of rigid frame is governed by columns and girders joined by moment-resisting connections. The advantage of rigid frame structure is this type of structure provide open rectangular arrangement, thus easy to fit window and doors. This type of structure is economical to about 25 stories only. Above 25 stories, the design will become uneconomical, as it will end up with large member sizes, which hence difficult to control drift. Rigid frame is suitable for reinforced concrete due to the rigidity of the reinforced concrete joint connections. In steel construction, the moment-resistant connection is costly. The design usually required different floor framing design, causing lowest stories have deeper girders. For this type of structural form, you will need to use approximate determination of member forces, due to gravity load day circumflex Euro 2 cycle moment distribution, column forces. Approximate determination of member forces, due to lateral load day circumflex Euro portal method, cantilever method. Approximate method for drift, A circumflex Euro components of drift, correction of excessive drift, effective shear rigidity. The next form of structural is infilled frame structure. Infilled frame structure is common in many countries. Usually, it is suitable for a building up to 30 stories high. Commonly, the structure is framing either from RC or steel beam and column, later infilled with brickworks, blockwork or precast panels. In which, as you can see in the figure, the infilled play a role in resisting forces and stresses in the infill and frame. In infilled frame structure, lateral load is resisted by the infill, behaves a strut along its compression diagonal to brace the frame. However, it is also depending on the quality of masonry brick used. This figure shows an example of infilled structure with RC beam column framing, infilled with brickworks. Meanwhile, this figure shows an example of infilled structure with steel beam column framing, infilled with blockworks. And this figure shows an example of infilled structure with steel beam column framing, infilled with precast panels. For this type of structural form, you will need to design of infilled structure, the frame and check the horizontal deflection of the overall frame. We have learnt 3 types of structural forms, namely braced frame, rigid frame and infilled frame structure. So, let's continue to learn another form of tall building structure. We all now learn more types of structural form. Another common form of tall building structure that you can consider to design a tall building is a shear wall structure. Shear wall structure is a continuous vertical wall structure, as highlighted in the shown figure. It is aesthetic in look and structurally capable of carrying vertical and horizontal loads. The function of a shear wall is to entirely resist lateral load. Shear wall is much stiffer horizontally than rigid frame. Application of the shear wall can go up to 35 stories. However, with the advent of superplasticizers and high-strength concrete, thus it is now possible to be used for taller buildings in the 50 to 60-story range. Shear wall is restricted openings in walls, thus suitable as residential. Shear wall structure performs well in earthquake because ductility is important in design of shear wall. The shape and plan position of the shear wall influences the behavior of the structure considerably. The walls are usually in C, I or L shapes, interconnected with coupling beams. Structurally, the best position for the shear walls is in the center of each half of the building. Arrangement 1 and 2 are some of the good examples locations for shear wall. Meanwhile, Arrangement 3, and Arrangement 4, can be considered as fair arrangement. However, Arrangement 5 and Arrangement 6 shows some of the poor arrangement for the shear walls. Shear walls, in high-rise construction, can be conveniently used around the cores for enclosing the building services. This figure shows an example of shear wall construction for steel frame structure. Practically, shear wall can be categorized into two, namely, proportionate and non-proportionate wall structures. The shear wall later can be divided into a circumflex proportionate and non-proportionate non-twisting and twisting structures. Stress analysis is the method that will be used to analyze shear wall structure. Another common form of tall building structure that you can consider when designing a tall building is a coupled shear wall structure. Here are the example picture of the coupled shear wall structure. Okay class, what is the difference between shear wall and coupled shear wall structure? The answer is, in coupled shear wall structure, the structure consists of two or more shear walls in the same plane, connected at the floor levels by beams or stiff slabs. Refer Fig 4.9. Coupled shear wall, usually used for residential building or building which have similar cross-sectional plan throughout. Meanwhile, in the previous said shear wall, the shear wall only consists of one shear wall, and not interconnected with the other shear wall in the same plane. Walls will behave and bend in the same centroidal axis of the walls. Thus the horizontal stiffness greater than in uncoupled shear wall system. Shear walls are more appropriate in reinforced concrete structure. When the walls deflect under the action of the lateral loads, the connecting beam ends are forced to rotate and displace vertically. Therefore, you can see that the beams bend in a double curvature and thus resist the free bending of the walls. The shear also induces axial forces in the two walls, tensile in the windward wall, and compressive in the leeward wall. Here is an example picture of a coupled shear wall. Okay, next is a wall frame structure. Wall frame structures is a combination of shear walls and rigid frames, as shown in figure. It is suited for buildings of up to 40-60 stories high. Wall frame structures is a combination of shear walls and rigid frames, as shown in figure. Without question, this system is one of the most popular system for resisting lateral loads. Nowadays, the systems has been used for buildings as low as 10 stories to as high as 70 to 80 stories. How does the wall frame structure behave? The frame basically deflects in a so-called shear mode. Meanwhile, the walls behave as flexural cantilever. Different deflected forms of walls and frames cause them to interact horizontally, shear wall frame interaction. Usually, this system is used in reinforced concrete structure. Figure shows an example of wall frame structure. However, use of steel in bracing and rigid frames offer advantage in horizontal interaction. We have learnt 5 types of structural forms, namely braced frame, rigid frame, infilled frame structure, shear wall structure and wall frame structure. So, let's continue to learn another form of tall building structure. We all now learn more types of structural form. Okay, now, we learn about frame tube structure. Frame tube structures is efficient framing system for tall slender buildings. In this system, the perimeter of the building consists of closely spaced columns connected by a relatively deep spandrel. The resulting system works as a giant vertical cantilever, and is very efficient, because of the large separation between the windward and leeward column. Lateral resistance provided by very stiff moment resisting frames. This stiff moment resisting frame, form tube, around the perimeter of the building, consists of very closely spaced columns 2 to 4 meters apart, joined by deep spandrel girders. This building is suitable in reinforced concrete or steel construction, with building from 40 to 100 stories high. This figure shows another example of frame tube structure. Figure shows tube-in-tube structure. This type of structure consists of an outer frame tube with an internal elevator service core. The hull and core are joined together to resist both gravity and lateral loading. If a steel type of structure is used, the core may consist of braced frames, whereas in a concrete structure it would consist of an assembly of shear walls. This type of structural form is notable, and, having been used for the Sears Tower, in Chicago. The Sears Tower consists of 4 parallel rigid steel frames, in each orthogonal direction. The frames are interconnected to form 9 bundled tubes, as shown in the figure. In the single tube structure, the frames, in the direction of lateral loading, serve as webs of the vertical cantilever. Meanwhile, the normal frames, acting as flanges. Here are the examples of Sears Tower. This is another type of frame tube structure. We call this as a braced tube. This system improved the efficiency of frame tube in increasing the building height. It behaves more like braced structure. The external brace improves performance of tube in carrying gravity load. Here are the example of braced tube structure John Hancock building. Okay, now, let's learn about core structure. In this type of structure, single core carry all gravity and lateral load. Meanwhile, for this type of core structure, slabs are cantilevered from the core. The core provide column-free perimeter at ground level, however, it is structurally inefficient in resisting lateral load. This type of structure will introduce warping. Example of tall building with a core tree structure can be seen in the Standard Bank of Johannesburg, South Africa, 1970. The building consists of floors, which are suspended from cantilevered arms in group of 10 floors. Okay, next is outrigger braced structure. This type of structure consists of central core. The central core can either be braced frames or shear walls with horizontal cantilever, or we call it as outrigger trusses or girders, connecting the core to the outer columns, as shown in this picture. When structure is loaded horizontally, vertical plane rotations of the core is restrained by the outriggers through tension in windward and compression in leeward, as can be seen in Fig 4.16b. You can imagine that the size of outrigger can be as large as 2-story depth, which is approximately 6 to 7 meters height. This type of structural system is most effective to increase structural stiffness for 40 to 70 stories height of building. Here is an example of detailed structural system with outrigger. And here is another example of the use of outrigger frame structure. The figure shows the overall high-rise structure, the detail of the outrigger system in the level, and the plan view. We have learnt 8 different types of structural forms, namely braced frame, rigid frame, infilled frame structure, shear wall structure, frame tube, outrigger braced and core structure. So, let's continue to learn another form of tall building structure. We all now learn more types of structural form. Next form of tall building structure is the suspended structure. Consists of central cores, with horizontal cantilevers at roof level with vertical hangers of steel cable, rod or plate attached. Architectural and ground floor free from columns is shown in Figure 4.17 to 4.18. Structurally inefficient in gravity load transfer should limit max no of floors to be supported by a single hanger to 10 floors only. This picture shows 2-tiered suspended structure. we can see there are two cantilever trusses, the first one supporting upper region of floors. Meanwhile, the second one supporting lower region of floors. Here is an examples of multi-story building with suspended floors. In this 12-story building, the floors are hung from the top of the central 82.3 meters high concrete core by 6 sets of continuous steel bridge cables. The arrangement of the cables can be seen at the top of the building. Floors were erected from the top down. The core is 11 meters x 11 meters in section and can be seen at both top and bottom of the building. This building is located at Vancouver, Barcelona, Canada. Okay, now let's look at the other form of tall building structure. That is space structure. Three-dimensional triangulated frame resist both gravity and lateral load as shown in Fig 4.21. Highly efficient, lightweight, simple concept. However, the space structures are geometrically complex, inclined members, etc. The structure commonly designed within a braced core for lateral loading resistance and in a region gravity load, which then all loads transferred through the space frame. Diagonalized grid structures have emerged as one of the most innovative and adaptable approaches to structuring buildings in this millennium. Based on the revolutionary structural concept for towers invented by Vladimir Shakha in the late 1800s, the use of diagrids as a contemporary formal structural language for tall buildings only started in the 2000s. Examples being Swiss Re in 2004 in London, the Hearst Magazine Tower in 2006 in New York City, and the Mogekun Cocoon Tower in 2008 in Tokyo. Nodal connections are the basis for the fabrication of three-dimensional space frame. The left figure shows the typical ball node connected joint. Meanwhile, the right figure shows the fully welded space frame for the Mandarin Hotel in Beijing, China. The left figure shows the diagrid. Within a diagrid is used to create central atrium spaces for the Capitol Gate Tower, and also for the Guangzhou IFC on the right figure. This type of structural system permits the floor system to span between the diagrid tubes. Both towers use reinforced concrete cores to assist with stability due to eccentric loads, in the case of the 18 degrees lean of Capitol Gate. The extreme height in the case of Guangzhou IFC, also contending with seismic and wind loads. On the Poly International Plaza Tower, the choice of concrete-filled steel tubes and the resultant node design responded to the elliptical plan of the tower. This type of a system requires all-welded connection, both for stability as well as to seal for leakage. It is necessary to have continuity of the void. This is to pumping of concrete through the node. At the left figure, the node is seen to be site-welded to the incoming diagonal members. To resolve, custom tapered tubes are fabricated between the tube and the plates at the intersection. At the right figure, the node in the fabrication shop. Reinforcing at the connection of the node to the tube permits the passage of concrete. This figure shows the Sony City in 2006, in Tokyo. The building used custom fabricated square hollow sections, in conjunction with castings, to create this innovative double-four paragraph diagrid project. This figure shows the square tubular frame for the Capitol Gate Tower drove a node connection that employed a crossing fabricated from plate steel to accommodate the multiple angular variations in the many nodes, while keeping the design aesthetic consistent. Okay, now, let's look at the last form of tall building structure. That is hybrid structure. Postmodern buildings with irregular shape, large cutout opening, facets, crowns, etc. Such as Turning Torso, Malmö, Sweden, Dubai Trump Tower. For these type of structures, engineer must improvise and combine basic structural forms in the same building. Sound knowledge of structural form and behavior is a prerequisite for hybrid structure. Here are examples of hybrid structure. As you can see, the structure is a combination of few basic types of tall building structural form systems. In this structure, the structure is built up based on the combination of frames tube on 3 faces of building, and space frame on 4th face. This is the end of part 2 session. Next is the last part, in which the video will show some examples application of the different type of tall building structures that have been practically applied in the existing current tall building in the world.